Okay, so we're sitting at a toll booth, and we're interested in the distribution of time it takes. How much time do we have between cars? How much time do we have to count our money and organize things and wipe down our stations so that we don't get the coronavirus? So we've got a sample of data, and the time between car arrivals at this toll booth, time t, ranges from 1.2 seconds all the way to 7.1 seconds. So we have 7 observations. Okay, so we know that inner arrival times typically follow an exponential distribution. It's just kind of from the theory. This is what our exponential distribution looks like. 1 over lambda e to the negative t over lambda. So the probability that our inner arrival time t takes on a certain value is a function of lambda. And so this is a 1 parameter PDF where lambda is the mean inner arrival time. So let's look at what our likelihood function is for this particular situation. So L of T1, T2, all the way to T7, and then our 1 parameter value is lambda. So because it's a product function, we're going to take the product from 1 to 7. So we'll have this PDF for each value of our observation. So 1 over lambda, there's only 1 parameter. EXP negative TI. So this takes on a value for each observation we have. So T1 is 1.2, T2 is 3.0, T3 is 6.3. So that equals, when we do all those products together, that equals lambda to the negative 7, right? Because it's 1 over lambda, and we're doing that 7 times, multiplying it by itself 7 times. And then when you do EXP times EXP times EXP, you end up summing everything, right, and the exponents. So it's lambda to the negative 7, EXP to the negative 1 over lambda times the sum of all of our times. That's in the exponent. So we just did the product 7 times, and this is what you get. Now, if we take the log of that, the log of L, we get, when you take the log of something with an exponent, the exponent comes down. So negative 7 log of lambda. And then when we take the log, or ln, of E, that just gets rid of that E, right? And so now we just have what's inside of that. And in which case it's negative, the sum of all the times is 35.3 divided by lambda. So this is our log likelihood function. And this is the sum of all of our inner arrival times. So our next step is to take the derivative of the log likelihood function, set that to 0, and then solve for lambda. And this will be the value of lambda that maximizes the log likelihood function. All right, so the derivative of the log likelihood function with respect to lambda, and this is our log likelihood function right here, is going to be negative 7 over lambda. So the derivative of log of lambda is going to be 1 over lambda. Plus 35.3 over lambda squared. So that was lambda to the negative 1, multiplied by negative 1. Now we have negative 2 as an exponent. Set that to 0. And then we solve. So we can factor out a 1 over lambda. So that gives us 35.3 over lambda minus 7 equal to 0. And then we get 35.3 over lambda equal to 7. Lambda equals to 5.04 seconds. So what we did is we took a data set, we created this log likelihood function, and then we took the derivative of that, set it to 0, and solve for the value of lambda that maximizes that function. And so this value of lambda is, you can consider it a probability weighted value of lambda. That creates an exponential distribution that is most probabilistically speaking, would fit the data. Know that you could also take this data and calculate lambda as the mean of the data. So what's the mean of all these values? Just grab a calculator and do that real quick. All right, so 1.2 plus 3 plus 6.3 plus 10.1 plus 5.2 plus 2.5 plus 7.1 divided by 7. So the mean of that value is 6.6. So if we did this from a method of moments perspective, lambda would be equal to 6.6. So you get a different probability distribution, and you calculate different probabilities of different arrival times based on these two different methods. So this is our maximum likelihood estimator of lambda, and in general, the maximum likelihood estimator, or MLE, of lambda is just simply the sum of t over n. Well, maybe I didn't do that right.
For my mean, I got 5.05.
Yeah, you know what? I didn't do that right. Great. Okay. So turns out, guys, that the maximum likelihood estimator is actually the same as the method of moments. Sometimes they're the same. Okay. Thank you, Michael. Sometimes they're the same. So sometimes when you do method of moments, it's actually the maximum likelihood estimator. Not always, right? So this is a very simple example. When we get into more complex, like log normal and stuff like that, the maximum likelihood estimator will be different from the method of moments estimator. So things get more complex with different distributions. So we will use functions in R to calculate the maximum likelihood estimators for different distributions. The maximum likelihood estimator is typically better or more accurate than method of moments. Sometimes it's the same for simple situations. But a big part of this is we've been assuming the distribution. So you still have to assume what the distribution is of your data. We assumed that this was going to be an exponential distribution for our inter-arrival times. Sometimes we might not know what the best distribution is. That's often the case for extreme value distributions. You don't necessarily know which extreme value distribution is going to fit the best. So next time in class, next week, we'll talk about how we know our distribution is a good fit, and we can look at different distributions, how they fit to the data, and then determine which one we think is the best distribution. Once you determine which distribution you think is the best, then you can go back and do your MLEs, your parameter estimation, and go from there.